Right, so here we've got question 4 from the CWC test. We've got a function here, x equals ln of sec y, and we are asked to find the derivative of that function in its simplest form. Notice that we need it as a function of x. At the moment we've got x as a function of y, so we're going to have to change things around a bit there. Also notice that in this function we've got a function of y within another function, so secant of 2y within natural log. So that suggests that I'm going to need to use the chain rule first of all to differentiate this, and when I differentiate this I'm going to get dx by dy. So I can say x is equal to ln sec 2y, and if I call u sec 2y, then I've got x equals ln u, where u equals sec 2y. I can differentiate each of these functions, so differentiate this one with respect to u, and I get dx by du equals 1 over u. Differentiate this function with respect to y, so I get du by dy, and if you look in your formula book you'll see that the derivative of sec 2y is 2 sec 2y tan 2y. I've kind of used the chain rule there a bit as well, taking the 2 outside. And then with the chain rule we can say that dx by dy is equal to this derivative dx by du multiplied by du by dy. In effect these du's are kind of cancelling, so if I substitute in what I've got, I get 1 over sec 2y multiplied by this derivative here, 2 sec 2y tan 2y. And at that point you will have got a method mark for using the chain rule. I can simplify all of that, and if you look carefully you'll see you've got sec 2y in the denominator and also in the numerator, so they will cancel and we end up with just 2 tan y. We can't always divide by sec 2y, for instance, in case this is 0. However, if you look at the range that we've got, y is between, the domain that we've got, y is between 0 and pi over 4, and throughout that range cosine would be positive, and so this is going to be positive. It's not equal to 0, as I've said there, so it's fine to cancel those. So we end up with dy by dx being 1 over tan 2y. So there I've just taken my dx by dy, which was 2 tan y, and found the reciprocal of it, dy by dx equals 1 over 2 tan y. So there was an accuracy mark if you got to this stage, and then another method mark once you'd found dy by dx in terms of y. But we haven't finished, because as I said earlier we were asked for dy by dx as a function of x. So we're going to have to change this function here to a function in x. So that's what we'll try on this next page. And what we do know is that we've got information that relates sec and x, and we've got tan here. So it suggests that we want to use some sort of relationship between tan and sec. And first thing we can do is just make sure that we get sec y in terms of x. So I know that x equals ln sec y, and I've just got rid of the ln by taking e to the power of both sides. So I've got e to the power of x equals sec y. I then, as I said, want to find some sort of relationship between tan and sec, and hopefully you remember that there is a relationship that we can gather from the sine squared plus cos squared identity. It might be that you already know of by heart the relationship between tan squared and sec squared, in which case you don't need to bother with this. But if not, then we can just remember that sine over cosine is tan. So if I divide through by cosine, then I end up with this identity here. And so I can say that tan y is equal to the square root of sec squared y minus 1. Okay, so that's given me a relationship between tan y and sec squared y. So I can now go back to my derivative here, and instead of tan y, I can write in what I know tan y is in terms of sec. Okay. So why have I done that? Well, basically because I know what sec 2y is in terms of e to the x. Alright, well in fact I know what sec y is in terms of e to the x. So I can replace my sec 2y with my e to the x. Actually, I think this should have been 2y, sorry, up here. So I can replace my sec 2y with e to the x, making sure I keep the squared, and then on my next line I can simplify this bit because e to the x squared is equal to e to the 2x. So this is the final derivative dy by dx, and it's in terms of x as requested. So that's it for that question. Definitely not an easy one, but hopefully you managed to get a few of those marks anyway. Thanks.